Englot from Stevens Institute of Technology, and it's my pleasure to be chairing the autonomous vehicle session. Each of the three spotlight talks that you'll be seeing was allotted 15 minutes. As you have questions, please feel free to type them into the Q&A or into the chat window, and we'll make sure that we have a couple minutes at the end to get to your questions. So let's start with our first speaker, Ming Zhou. You and your co-authors, I think, are on the panel now. Can one of you try sharing your screen?
Does that work?
Yes, I can see it. All right. Well, the floor is yours.
Okay, thanks very much. So my name is Julian, and together with Ming, we're some of the co-authors on the paper SMARTS, which stands for Scalable Multi-Agent RL Training School for Autonomous Driving. So SMARTS is a simulation platform, but why are we building yet another simulation platform? Well, despite over a decade of R&D and millions of miles driven by autonomous vehicles, still how to competently interact with diverse road users remains an unsolved problem. If we look at the example here on the bottom right, we have what's called the double merge scenario, or the double merge task. Vehicles from the left need to make their way to the right, but have to cross the lane to do so. And here's another example over here. So with something like this, it sort of seems it's a simple task, but it still involves a fairly complex interaction. Vehicles need to weave into small gaps to make their way into the other lane. And if an autonomous vehicle is unable to do this, sort of don't expect to be coming home anytime soon. Then we have this other extreme example here on the top right of how complex interaction can get. Now, current L4 or mainstream L4 autonomous driving solutions, they're limiting interaction rather than trying to embrace it. And our view is that this is actually a multi-agent problem and it requires multi-agent learning. So given that our contribution here is an industrial strength simulation platform to bring the multi-agent learning to autonomous driving, an approach to bootstrapping realistic interaction or the bootstrapping problem, an approach to scalable multi-agent computing, and a benchmark suite to tie everything together. So I want to highlight one main design goal of SMARTS, and that's about realistic interaction. So this loop, we start off with a diverse set of agents. That can be, let's say, rule-based agents from scripts. It could be more complex learning-based agents. It could be classical control or community contributions, let's say from a competition. We take these agents and we provide them or host them through the social agent zoo. Its job is to basically package and serve these agents. Then they can be pulled into scenarios and perform self-play with each other. Then we can collect that data and use that for generational rounds of training on these agents to sort of increase the competency of these diverse set of agents. And they can be as simple as sort of a few line rule base or as complex as a full autonomous driving stack. Now, the SMARTS platform is a compositional one, so it follows a compositional architecture. We orchestrate, or the SMARTS platform orchestrates stepping of co-simulators, such as Sumo for background traffic, Bullet for realistic physics, and many others. And SMARTS' job is to take their view of the world and make sure that they're harmonized in a coherent way to put together the final simulation. So Sumo might want to put a vehicle in a certain location, but that's not physically possible according to Bullet. So SMARTS is trying to make sure that the final result is coherent. Scenarios are compositional between maps, traffic flows, actors, and other primitives of building a scenario. And finally, bubbles is a concept we're putting forth on how to bring agents into the interaction scenario. And bubbles are spatio-temporal regions where at those regions, the social vehicles are expected to be controlled by an agent. And we'll talk more about that shortly and how that helps with the sort of distributed scaling up problem of autonomous driving. Now, finally, distributed computing underpins everything we have here. So agents, both at the agent and instance level. Agents can operate on their own machine if it's something that's requiring more computation, or you can have multiple agents running together with multiple instances on one machine. It totally depends on the individual's need for training and evaluation. Now there's Scenario Studio. So Scenario Studio is a Python package for developing scenarios. And it provides a DSL to describe scenarios at sort of the logical level. And we have an example here. So within about 25 lines of code, we have traffic that can be defined. So vehicles operating on a route at a given rate, and you can define different distributions of actor types. Then there's missions for social agents and ego agents. And all these concepts here are parameterized to support things like domain randomization. And this 25-line snippet generates what you have here at the bottom, social traffic or background traffic moving from west to east with an ego vehicle making a left turn. And you'll notice here there's a reference here, the agent locator, to an RL agent. And this here is an example of how Scenario Studio, your scenarios, can reference community sourced agents from the agent zoo that we spoke about earlier. And the last point I want to mention before moving things over to Ming is about bubbles. So what are they and why do we need them? Well, complex driving tasks likely require quite computationally expensive agents to navigate those tasks. And bubbles are a mechanism to allow us to focus computational resources where it actually matters. So on the meaningful interaction. So given this example here on the right, we have vehicles on this highway portion that eventually make their way into the junction. When they're outside of the junction, they can be controlled by background traffic providers. And then, which is computationally low in terms of resources. Then once they make their way into the bubble, this region here, the agent can take over, navigate that task to completion, collecting data and learning from the experience. And then once the vehicle exits, control is handed back over to the background traffic provider. So this primitive here really allows us to scale up compute and focus the computation on where it really matters. And these bubbles can be fixed and also pinned to vehicles in a traveling way to support different types of scenarios.
Okay. As a natural technique to solve the multi-agent interaction problem, multi-agent reinforcement learning has been researched for many years. So it is a straightforward idea to use it to dig out the effects of agent interactions in autonomous driving. Key elements are listed in this slide. There are baselines, metrics, scenarios, and programs for training and evaluation. Now I will introduce them to you in the next minutes. And our target is to train and evaluate the multi-agent learning algorithm with some given metrics and scenarios. For multi-agent learning, training efficiency and scalability is always a critical aspect. And also for its application in autonomous driving. To support these requirements, we've integrated three popular multi-agent reinforcement learning libraries. They are RLib, PyMAR, and MyLib, respectively. In summary, with the support of these libraries, we can easily train or evaluate multi-agent algorithm. Generally speaking, the multi-agent RL algorithm can be classified into 6 paradigms in different learning manners, as shown in the table. Well, from the perspective of interaction, we can also categorize them into non-interaction, partial interaction, and global interaction, respectively. As a benchmarking, a more comprehensive set of algorithms will be more interesting and functional. But the integration of these three libraries cannot satisfy this requirement. So in our current implementation, we cover these paradigms and give some typical algorithm from them, and you can get more details from our paper and the code repository. We noticed that the existing metrics for the multi-agent reinforcement learning research on autonomous driving tend to be limited to specific tasks, as the collision rate and the completion rate introduced in the model performance block. But for multi-agent learning, an algorithm performance is not only a matter of how it itself behaves, but also involves other agents. To support that, we propose more metrics, including agent population behavior metrics and game theoretical analysis. Especially the population behavior metrics, we are the first one to evaluate the driving performance from the perspective of behaviors. Okay. To validate the functionality of benchmarking, we conducted some experiments on 3 increasingly and more challenging driving scenarios. Both of them require non-trivial interactive capability to be learned, and agents in each scenario will be assigned with different dimensions. Specifically, they are required to drive from a specific start to a specific goal. The tested 7 baselines cover 3 different multi-agent reinforcement learning paradigms, and the evaluation focus on both macro performance and behavior analysis. Okay. And compared with independent learning algorithm like DQ and the PBO, most of the others tend to be a lower collation rate and a higher combination rate. Because of the consideration of agent induction, we use radar plots to analyze the behavior difference between the algorithm and the scenarios. For example, in the two-way scenario, the behavior difference concentrates on the diversity, and in the other two, the behavior difference covers both the diversity and the safety. Generally speaking, we have the knowledge of what behavior preference should the agent perform. For example, in the two-way scenario, it is obvious that a narrow diversity behavior means it will be driving smoother, because turn right or turn left will have a lower frequency than the speed change. So a high diversity may be lead to unnatural driving behavior. So it also it was noting that though we showed the result from the perspective of multi-agent reinforcement learning, we think OR smarts can also be used to do more research. For example, such as robust learning or safe RL for multi-agent for autonomous driving. Also the population-based learning for autonomous driving. Okay.
Okay, thanks very much. And we're very proud and excited to share that Smarts has recently been open sourced. It's a sort of a multi-year effort to put this industrial grade simulation platform together. And we encourage and invite you all to take a look and see what Smarts offers for itself. Thank you very much.
Thank you. Please feel free to post any questions in the chat or the Q&A. In the meantime, while we wait to see if any attendees have questions, perhaps our next speaker can try sharing their screen. Okay, one question has appeared in the Q&A. What's the difference between the different agents? For example, the optimal agents versus the other ones?
Sure, I can answer that. So these agents can be community sourced. So they can be defined as you wish. You can develop your own agent that is, let's say, classical control using optimal control methods, or you could, which is just classical methods, or you can provide an agent that's maybe based off a deep neural network. It's really up to the researcher how they want to define their agents. The interface is fairly slim, and it's really about them and their own design.
Okay, thank you. That appears, oh, there is one more question. Let's take this as the last one. Does the platform support fast data collection through its simulation?
Yes, happy to say it does. That's the primary concern of Smarts. It's to support efficient data collection and also to scale up data collection. So if you have the compute, you can do it as fast as you want, basically.
Okay, and since we're out of time, I think the panelists can address individual questions that continue to come up in the panel chat here. I think we need to move on to our next presentation. Raris Ambrose from Toyota Research Institute will be presenting self-supervised 3D keypoint learning for ego motion estimation. The floor is yours.
Yeah, hello. Can you hear me?
Yes.
And can you see my slides?
Yep.
Perfect. All right. Thank you, Brandon. So good morning, everyone. And hello, my name is Raresh, and it's my pleasure to present our work titled Self-Supervised 3D Keypoint Learning for Ego Motion Estimation. And this work was done in collaboration with Jay Shong and Patrick from KTH, as well as my colleagues from TRI, Vitor, Sudeep, Hanmei, and Adrian. In this work, we propose a novel self-supervised learning scheme for 3D keypoint learning. And in particular, we learn how to regress keypoints that are both texture as well as depth aware. And we demonstrate the usefulness of our method on the task of ego motion estimation or visual odometry. Right, so our method is motivated by three underlying threads. We build on the concept of self-supervised learning, whereby we try to leverage and learn from large amounts of unlabeled but structured data. And so while curating labeled data can be tedious, difficult, or expensive, unlabeled video data is really very easily available, as cameras tend to be abundant in a wide variety of scenarios. Second, we're interested in keypoints, as they have been widely used to represent salient points in images, and finding and matching these keypoints is essential, since the associated correspondences can then be effectively used for scene reconstruction and camera pose estimation. And moreover, for traditional methods, the keypoint detector and descriptor are typically handcrafted and thus have limited invariances to illumination or perspective changes and so on. However, recent methods have shown that learning techniques can be used to improve the detection and matching procedure. And in this work, we're particularly interested in self-supervised learning, the reason being that keypoints are almost impossible to label, because the optimal key points for different scenarios are case dependent, and it's difficult for human annotators to really identify the optimal key points. So on the other hand, by leveraging a large amount of unlabeled data and incorporating domain knowledge into objective functions, we hope to be able to tailor our key points and to achieve better performance given a downstream task, which in our case is visual odometry. And finally, we're interested in predicting dense monocular depth from images, as understanding scene geometry is one of the fundamental capabilities of any robotic system. And while depth from a single image is fundamentally an ill-posed problem, recent research has shown that structure from motion and photometric consistency in videos provides enough information to accurately learn to predict scene depth from monocular videos without any human labels. So our work builds on two related work streams. First, we leverage self-supervised keypoint work that uses randomly generated homographies to augment input images, imposing consistency constraints on the resulting image pairs. And specifically, related work such as superpoint and unsuperpoint, as well as our own prior work, have explored the idea that single images can be used to train discriminative keypoint networks without any source of supervision. And as an example on this slide, we have the source image on the left. We generate a random homography, and we augment the image, obtaining a target image, as can be seen on the right. And we extract key points on these two images, and we use the generated homography, which acts also as ground truth, to impose consistency or geometric constraints between the two images. And second, we build on related work in monocular depth, whereby given two images, a target and a context image, we predict dense per pixel depth from the target image. And using the context image, we synthesize the target image using the depth and the estimated ego motion. And using the context image, we derive a proxy per pixel, dense per pixel photometric loss, which is usually a combination of an L1 and structural similarity patch-based loss, which allows us to derive the training signal. And importantly, the view synthesis operation is done using spatial transformers, making the whole operation differentiable end-to-end. And the image on the right-hand side of the slide shows the output of a typical monocular depth network. And we see that given the RGB image on the top left, the predicted depth on the right, on the bottom, sorry, and the reconstructed point cloud on the right, accurately follow the or accurately represent the scene geometry, and are able to recover and to capture fine details such as poles, trees, and so on. Right, so putting these together, our paper extends related work and generalizes prior self-supervised keypoint learning methods to videos. And specifically, we propose a pipeline for keypoint detection, matching, and 3D lifting in videos. And our aim is to train keypoints that understand scene texture as well as scene geometry. And we note that previous methods that operate on single images are limited in the kind of invariances they can capture, as the scene is only manipulated via homographies. On the other hand, in our work, we propose to train two networks to regress keypoints as well as depth. And to optimize the whole system jointly, we propose a novel differentiable pose estimation module based on the orthogonal Procrustes algorithm. And specifically, the way we do this is, given consecutive images in a video, we extract keypoints, we compute correspondences, and we use the correspondences to estimate an SE3 pose that tightly couples the whole system together. And as our final contribution, we also show that our keypoints can be integrated into state-of-the-art tracking algorithms, such as direct sparse odometry or DSO. And we show that we achieve state-of-the-art results compared to other methods that use monocular data. And finally, the images on this slide show the typical output of our system, with the top row showing keypoints that are matched across consecutive frames in a video. And the bottom row shows the corresponding depth as estimated by our system. And we note that the keypoints are color-coded, and the color coding indicates the perceived depth of the keypoints in the scene based on how we estimate it with our method. And we also note that the keypoints are able to match the dominant scene motion or ego motion, as well as the motion of individual dynamic agents in the scene. Okay, so at the high level, our pipeline optimizes two different networks. We have the keypoint net on one hand and the depth net on the other hand, and we impose a combination of geometric losses and photometric losses. And everything is tied together by our differentiable ego motion formulation. So diving a bit deeper, first we use the keypoint net to extract keypoints from both the target frame and the context frame, as indicated by the red and blue circles on this slide. Additionally, we predict dense per pixel depth from the target frame using the depth network, and we associate a depth measurement with each target keypoint. Next, using associated descriptors, we compute correspondences between the target keypoints and the context keypoints, as indicated by the dashed lines connecting the red and blue dots on this slide. And we know that at this stage, we compute a set of 3D points in the target image and the associated 2D points in the context image. So given these 3D, 2D correspondences, we use the perspective endpoint algorithm, or PNP, to compute the transformation between the two frames. However, the issue is that this operation is not differentiable. Traditionally, the PNP algorithm is not differentiable, which is not an issue at test time. However, at training time, we want to be able to propagate gradients throughout the pipeline. And therefore, we propose a differentiable method based on the orthogonal Procrustes algorithm, which we use to derive a 3D loss based on 3D correspondences. And the way we achieve this is we first lift the context keypoints to 3D by using the depth of the target keypoints reprojected into the context frame via the PNP pose estimate. And then we minimize the resulting 3D loss in closed form by first estimating the rotation through a singular value decomposition, or SVD, following which we estimate the translation also in closed form. And we present detailed derivations for these operations in the paper. But the important thing to note is that this makes the pose estimation module or the ego motion estimation module differentiable, allowing us to propagate gradients throughout the pipeline. Right, so given the context points in blue and the reprojected points from the target image in red, we impose an L2 loss, which aims at minimizing the reprojection error, which is as indicated by the geometric loss box on the slide. And simultaneously, we also use the estimated ego motion to synthesize the target image in the frame of reference of the context image, which allows us to induce per pixel photometric loss. And I'll just briefly mention that each one of these loss terms is in fact made up of three separate losses. So we have the key point, descriptor, and score loss for the geometric term, and we have the smoothness, consistency, and photometric loss for the appearance or photometric term, with detailed definitions and derivations also given in the paper. And for our final contribution, we demonstrate the usefulness of our method by plugging it into DSO. And so on this slide, we're just showing a high-level outline of the method, and the dashed boxes indicate the components of DSO that we modified. Specifically, we modified the depth initialization of keyframes using our predicted depth, And we also modified the DSO feature tracking to use the features that we estimate using our method. Right, so we show quantitatively that our method achieves state-of-the-art results when compared to other methods, and specifically we compare to methods that use monocular data at test time. And in the paper, we show detailed results on Kitty. We estimate the performance of our keypoint networks on H patches, and we also estimate the performance of our depth prediction networks. And I'll just mention that when we integrate our keypoints with DSO, we achieve state-of-the-art results compared to monocular methods. And we know that our performance, and particularly our orientation estimates, are closing the gap with methods that are trained on stereo images such as DVSO. And particularly, while DVSO is using monocular data at test time, they're trained on stereo images, which allow them to leverage stereo constraints and which provides very strong priors for outlier rejection during the tracking phase. And by comparison, our method is trained just on monocular data and evaluated on monocular data, which is implicitly a harder problem. We also show qualitatively that when we integrate our key points with DSO, but as well as our frame-to-frame tracking results, our resulting trajectories are able to track the ground truth trajectory quite well. And in addition, we also compare to the very popular MonoDep2 framework, which basically learns depth and ego motion in an end-to-end fashion using neural networks. And we know that so MonoDep2 is indicated by the red plot on this slide. Our estimates, even our frame-to-frame estimates, track the ground truth trajectory quite well and accurately. And finally, I'll just show a brief clip of our system in action. I don't know if you can see it. I hope you can see it. So this is our system running on one of the Kitty sequences, and we show the flow of inlier key points on the left, the corresponding depth in the center, and then the number of matched key points and inliers on the right. And I'll mention that our networks run real time, basically at 30 FPS on images of 640 by 192 resolution. Okay, so in conclusion, we propose a novel self-supervised pipeline for regressing depth-aware key points from monocular videos, and we achieved this by training jointly a key point and a depth network tied together through a differentiable pose estimation module. And we showed through integration with DSO that we can achieve state-of-the-art monocular viewer results. Thank you for your attention, and please let me know if you have any additional questions.
Thank you. It appears that so far we have one question in the Q&A. Is the approach going to be open sourced?
Very good question. Yeah, we're working on that. We're working on that. So hopefully in the next few weeks.
Okay. While we wait to see if any other questions appear in the Q&A, perhaps our next speaker can try to share his screen. And yes, it appeared we have one other question. Do you preserve the absolute depth in the key points?
No, so in monocular VO, the depth is accurate up to a factor of scale. And so we concatenate the predictions, and then to obtain our results, we perform a symmetry or a symmetry alignment step at the end.
Okay, thank you. And it
I'm
appears
not sure if that answers the, yeah, I guess.
Yeah, I suppose it appears that it has. Yes, thank you. Okay. There are no other questions listed at the moment, but let me also just take this opportunity to remind you that all the speakers from this session will be available during the parallel interactive sessions later in the day. So please feel free to take advantage of those as well. And I guess we'll move on now to our next speaker, Sean Siegel from Uber, who will speak on universal embeddings for spatio-temporal tagging of self-driving logs. Sean, the floor is yours.
Thanks. Hi, everyone. I'm Sean, a research scientist at Uber ATG. And today I'll be presenting our work on universal embeddings for spatio-temporal tagging of self-driving logs. Self-driving companies have accumulated massive databases of raw data logs from driving millions of miles in the real world. To leverage this data effectively, it is helpful to have tags as metadata associated with each data log. These tags have many useful applications. For example, they can be used for the rapid curation of better training data sets, efficient retrieval of scenarios for simulation, and insightful failure analysis through the visualization of the tags most correlated with the system's failures. Let's consider some potential approaches for generating these tags. The simplest option is for humans to manually tag self-driving scenes. While this approach can be effective for small data sets, it is far too expensive to scale to databases containing millions of miles. Alternatively, the outputs from the onboard perception system could be reused to heuristically reason about different scenarios based on the detections over time. Unfortunately, this approach requires extensive engineering, often returns noisy results, and cannot generalize to many scenarios that require reasoning about more than the detected actors. Motivated by these challenges, we present our approach, which takes only raw sensor data as input, yet remains a general framework to tag any attribute in a self-driving scene. We approach the problem of spatio-temporal tagging by learning a function f, which takes a data log and a tag attribute tau from a predefined set and returns spatio-temporal tag values. Tag values are tensors with both spatial and temporal dimensions and can represent any value, discrete or continuous, in the self-driving scene. For example, if we are interested in tagging vehicle density, each tag value would represent the vehicle density at a specific location and time step in the original data log. Tag values can later be pooled to generate interpretable scene tags, for example, tagging the vehicle density in front of the SDV. Next, we provide an overview of our approach for learning F, using a universal embedding to tag all attributes. Our log embedding network takes a series of voxelized LiDAR sweeps and a rasterized HD map as input. Because logs can have arbitrary length, our network is fully convolutional across time. Here, we visualize the network for a single time step. Both inputs are first processed by independent backbones. Then map and LiDAR features are concatenated and passed to a convolutional header to produce a spatio-temporal embedding. Now imagine we want to tag all vehicles turning left in the scene. First, we encode the tag attribute tau, represented by a row in a learnable matrix A. Using a simple element-wise dot product, we combine the log embedding and the attribute embedding to obtain a spatio-temporal tensor of tag values V. Our model can also be extended to support compositional functions, which take tag values from multiple attributes as input and return a new tensor of tag values. Compositions enable our model to naturally handle more complex tags that relate to multiple attributes. For example, tagging vehicles turning left at a four-way intersection. Our approach is trained end-to-end over all logs in our training set. For each time step in a log, we minimize a supervised multitask tagging loss over all discrete attributes and continuous attributes. For discrete attributes, we apply a cross-entropy loss across tag values, and for the continuous attributes, we use a smooth L1 loss. Naively optimizing this loss will be suboptimal, given both large imbalances in the tag value distributions and the multitask nature of this objective. To overcome the largely negative tag values, we apply hard negative mining, taking the loss of only the k hardest negative examples for each positive example. This ensures that for each tag attribute, the distribution of tag values used during training is balanced. However, it also creates imbalances between the supervision each attribute receives, as commonly appearing attributes, like parked vehicles, will contribute more regularly to the loss than rare attributes, like lane changes. Therefore, rather than sampling logs uniformly, we introduce a task balancing scheme which constructs mini batches by first sampling an attribute uniformly, then sampling a log that contains at least one positive example for that attribute. We evaluate our model on a new large-scale dataset, SDV scenes, with sensor observations, HD maps, and annotations for 15 diverse scene attributes. Let's consider the scene attributes in more detail. First, for any spatial region, we can tag the vehicle or pedestrian density, which we choose to represent as a continuous attribute to handle actors that are partially inside a spatial region. Here, we show an example of a particularly dense scene with many vehicles and many pedestrians. These scenes can be particularly interesting for the evaluation of prediction and motion planning models. We also consider the actions of all vehicles in the scene. This includes whether each vehicle is stopped, braking, parked, lane changing, or turning. In addition to actions, we consider two vehicle-to-vehicle interactions, whether a vehicle is stopped for or braking for another vehicle. These interactions can be particularly relevant for the retrieval of safety-critical self-driving scenarios. Along with these discrete attributes, we also consider continuous attributes of the scene, such as each vehicle's current speed. Finally, we consider tags which relate to the map's topology. For any intersection in the map, our model is trained to tag its type. Let's move on to some examples of qualitative scene tags produced by our model, given only the raw sensor data shown on the left and the HD maps, not the extra bounding boxes shown for visualization purposes only. Tag 1, vehicles in the scene. Our model, 21, ground truth, 21.8. Pedestrians on a crosswalk, both our model and the ground truth tag 1. Vehicle turning left in the intersection, both our model and the ground truth tag yes. Maximum vehicle speed in front of the SDV, both our model and the ground truth 10.9 meters per second. Let's move on to one more scene. Maximum vehicle speed behind the SDV, our model 14.2 meters per second, ground truth 13.5 meters per second. Vehicle density around the SDV, our model 13, ground truth 13.2. Vehicle blocked by vehicle in front of the SDV, both our model and the ground truth tag yes. Four-way intersection in front of the SDV, both our model and the ground truth tag yes. We also evaluate our model in the retrieval setting, returning logs with a desired tag value. For example, in the first row, we show scenes tagged with vehicle density greater than 10 around the SDV. In the second row, we show scenes tagged with a three-way intersection in front of the SDV. Finally, in the last row, we show scenes where there is a vehicle tagged as turning in front of the SDV. Quantitatively, we see that our model simultaneously attains good performance across the continuous attributes of actor density and vehicle speed, measured by L1 error, map topology attributes, measured by F1 score, and the actions and interactions, also measured by F1 score. We ablate each model input to understand the relative gain of adding LiDAR and HD maps for each tag attribute, summarizing the performance across tag types with a geometric mean. Given only the map, we notice poor performance across most attributes, other than map topology tags and the parked vehicles tag. Given only LiDAR observations, our model can reasonably tag actor density, vehicle speed, and certain vehicle actions, which can primarily be inferred from vehicle motion, such as turns. We see the best performance across all tags when the model is given both LiDAR and HD maps, and notice that certain tags like actor density and lane changes benefit considerably from leveraging both inputs simultaneously. We also compare our approach, which learns a single embedding for all tag attributes, against one where the embedding is separated by attribute type. 1, actor density, 2, vehicle actions and interactions, 3, vehicle speed, 4, map topology. For the separated approach, we use an independently trained model to learn each component of the embedding, requiring 4 times the model capacity. To summarize the system performance across tags, we again use the geometric mean. For simplicity, here we summarize the metrics across all continuous and all discrete tags to represent the performance of our system by only 2 numbers. Our results show that for small embedding dimensions, our joint model clearly outperforms a separated embedding across both discrete and continuous tags. In fact, we found the separated model was unable to learn to tag actor density due to limited embedding memory, resulting in extraordinarily large errors. As we increase the embedding dimension to 16, we continue to see our approach outperform the separated approach. These results showcase that our model effectively learns to use the dimensions of the embedding space better than using human priors to separate the embedding based on tag attribute types. Finally, given a large enough embedding memory, both approaches perform similarly. However, our approach is still preferred to the separated approach, as it requires 4 times less model capacity since we do not require independently trained models. In a real-world setting, the tags that need to be supported by our system will grow as requirements change and new supervised data becomes available. Ideally, models should support continuous learning, in which new tag attributes are trained on top of a learned model. Here, we explore whether our learned embedding can boost performance for new related attributes. For this experiment, we introduce an additional set of 4 attributes related to vehicle-to-vehicle interactions. We tag vehicles that cause another vehicle to be blocked or to brake. We also consider if the vehicle specifically causes the SDV to be blocked or to brake. In blue, we show the performance of a baseline model trained independently on each attribute. Here in red, we show the performance of our joint model that is first trained on the original 15 attributes and then trained on the 4 additional attributes in a later stage, simulating the continuous learning setting. Our model always outperforms the independently trained baseline and can provide up to 45% increase in F1 score. Importantly, our continuously trained model maintains similar performance on the original 15 attributes. We examine the effect of our task balancing scheme compared to training by sampling logs uniformly. Here we plot smooth validation metrics over the course of training and notice that our balancing approach leads to faster convergence and better performance across both continuous and discrete tag attributes. Finally, we show a t-SNE visualization of the universal embedding space. Each point corresponds to embedding vectors at spatial locations with vehicles. We color each point with the primary action or interaction of that vehicle. 3 dominant clusters are apparent: vehicles keeping lane, stopped vehicles, and parked vehicles. We also see smaller clusters appear for more rare actions, such as left turns and right turns. This visualization demonstrates that our learned embedding captures the high-level semantics of each spatial location. In conclusion, in this work, we introduced the task of spatio-temporal tagging of self-driving scenes. We proposed an approach capable of tagging a varied and complex set of scene attributes related to real-world self-driving scenes. Our approach learns a universal embedding for all tags with strong generalization properties demonstrated in the continuous learning setting and a semantically meaningful latent space. There are many exciting future directions to explore. Future models should explore leveraging information from more sensors of the SDV, including camera images and radar captured by the vehicle. Future models can also use more complex modeling techniques to enable better spatio-temporal reasoning. Finally, we are excited by the prospect of learning a set of compositional functions in order to improve the performance of the system on compositional tags. Stay tuned for a public benchmark on this task, which we plan to release soon. Thanks for listening.
Thank you, Sean. If you have any questions, please feel free to post them in the Q&A. You may have noticed we've disabled the chat functionality so that all the questions end up in the same place. And since we have a couple minutes remaining, we can wait to see if anything appears in the Q&A. And in the meantime, let me remind everyone again that you'll have an opportunity later today as well to speak with today's Spotlight Talk speakers during the parallel interactive sessions. Well, it appears we have no takers on this one. Nonetheless, I hope you'll all join me virtually in thanking Sean for his talk. And this concludes the autonomous vehicle session. The conference program will resume at the top of the hour with our first tutorial. Looks like one question finally appeared, so don't go anywhere just yet. Have you tested generalization capabilities across different data sets?
Yeah, thanks for the question. We've mostly worked on this new data set that we introduced due to the cost of basically generating these scene attributes. It's pretty expensive. So right now we've only tested it with this data set, and there's no other data sets with the same set of attributes right now. But in the future, this will be something that we can look into. Thanks.
All right, well, it appears that's all we have in the Q&A for now. Thanks again, Sean. I guess we'll conclude our session there. And as I mentioned, we now have a break in the program, and the conference program will resume at the top of the hour. Thanks everyone for participating in this session.